Welcome back, everyone. And before we get started at looking at the calculations, I just want to mention, now that I'm looking at the photo here, so these modules are installed in landscape, right? The long edge of the module is kind of the lower leading edge versus being installed in portrait. Now, in-a-row shading can have greater effect if the modules are in portrait. So take that into account. Regardless of how the modules are installed, we want to avoid in-a-row shading, but if they are in portrait, the effects of shading can be much more severe and detrimental to production. Okay, with that, let's get into calculating inter-row shading. Let's continue and look at how do we calculate the distance between rows. We're taking into account, again, what we're calling inter-row shading. Here we have a couple crazy diagrams, but we're going to walk you through it. On the left is what we're calling step one. Here we're going to calculate the length of the shadow from the sun in the early morning from one row of modules. Okay, as the diagram shows, we have H is the height of the tilted module. We have L is the length of the shadow cast by the sun. That's actually what we're going to solve for. X is the altitude angle of the sun in the morning. And in this instance, for step one, we have to get our 3D mind working. So the sun might be considered outside in front of the screen, and the length of the shadow is going into the screen because the sun's rising in the east in the morning and casting a shadow that goes from the array, from the top edge of the module into the page. And if you look at step two, it kind of makes it a little more clear for the length of the shadow that we're talking about in the early morning. In step one, we're going to calculate the length of the shadow. It depends on the altitude angle of the sun and the azimuth angle of the sun at a certain time of day. Once we calculate the length of that shadow, then we can move on to step two and also use trigonometry to determine the distance between rows that we're showing in green, labeled as D. That overhead view in step two, now we can get back to 2 dimensions, and we're looking straight down on the array. The L, the length of the shadow, is what's cast by the sun in the early morning or late afternoon. And the azimuth angle is Y, which we get from our sun chart, but we have to determine what that small y is in red, and we'll show how to do that in step two. And we're going to dive right in and do an example with an example array and an example sun chart. For this example, we have a ground mount that's located at about 36 degrees north latitude. So we have a sun chart from 36 degrees north latitude. This array, there are going to be 3 rows of modules. They are facing true south and they're on a flat plane. Perhaps it's flat ground, perhaps it's a flat roof. Our goal is to have no in-a-row shading from 9 a.m. to 3 p.m. any day of the year. We're going to say that's our solar window of 6 hours, right? 9 a.m. to 3 p.m. A few more array details. The H, the height of the modules, is going to be 2 feet. And looking at our sun chart, we see our azimuth angle at 9 a.m. on December 21st is 138 degrees. And we see our altitude angle is 17 degrees at 9 a.m. on December 21st. So we're going to use those 3 numbers in our following calculations. So step 1, we have to determine the length of the shadow at 9 a.m. And in the lower right, we have those values already. We have the vertical height of the modules as 2 feet. Remember, I'm not concerned about any of the racking underneath. It's just the tilt of the modules because we're on a flat surface. So the vertical height of the modules, h, is 2 feet. The altitude angle, x, of the sun is 17 degrees above the horizon. The azimuth angle, y, of the sun is 138 degrees. So that is a little south of east. Remember, this is from December 21st, the worst case design day in the northern hemisphere. So remember, we need to think in 3 dimensions, and L is the shadow cast that's actually going into the screen. And the sun is out front because it's in the east, early morning, and our L is going into the screen. So we need to calculate the shadow length L at 9 a.m. Let's go back to trigonometry. Quick review, tangent of an angle is equal to the opposite portion of the triangle over the adjacent leg of the triangle. So tangent equals opposite over adjacent. In our diagram here, tangent of x equals height over L, but we need to solve for L, so that becomes L equals height divided by tangent of x. And now we just plug in our numbers. We have L equals 2 feet divided by the tangent of 17 degrees. So 2 feet divided by 0.3057, we get a shadow length of 6 feet 6 inches. That's at 9 a.m. on our worst case design day of December 21st. Our length of shadow from the array going into the screen is 6 feet 6 inches. Please feel free to rewind, review this section, read the notes. Trigonometry can be quite challenging, especially when I'm talking in 3 dimensions, but I hope I walked you through it enough and we can move on. And now in step 2, we need to calculate the minimum distance between rows. And we're gonna use that shadow length from 9 a.m. to determine our row spacing of D in green. And you can see in our diagram on the right with the sun, let's say that is rising in the east, and now you can see how it was casting that shadow of L. Previously it was going into the screen. Now that we're looking down on the array, we can see that the sun comes up in the east. It casts a shadow from right to left, represented by L. And now we're going to use that value L to calculate the row spacing. Again, our parameters that we have are given in the lower right. The height of the modules is still 2 feet, altitude angle of x, azimuth angle of y, and length of shadow L. Notice we do have a small y in red, and that's going to help us out to perform our trigonometric functions to determine D. To determine angle small y, we draw a straight line from the sun's path through L. We know that's a straight line, and we subtract the azimuth angle to determine that angle y. So in this case, we have 180 degrees from our straight line. We subtract 138 degrees, which is our azimuth angle. That gives us an angle small y of 42 degrees. And that's what we just did there. We determined our small y angle. Now we go back to trigonometry, and cosine is the adjacent leg of the triangle over the hypotenuse. Okay, so cosine small y equals distance between rows divided by that shadow length L. Well, we can solve for D. So D equals cosine small y times L shadow length. We can plug in our numbers. cosine of 42 degrees times 6 feet 6 inches, or 0.743 times 6 feet 6 inches gives us a distance between rows of 4 feet 10 inches. I hear you. There's a lot of trigonometry here, but it's pretty simple. And really, you don't have to fully know trig, just have to know what values to plug in. So again, I hope I walked you through that. Please review this, read the notes contained with each presentation and each slide, and certainly use your online instructors if you're struggling with this section. Now that we've determined the row spacing between rows as 4 feet 10 inches for this example, let's go ahead and look at our total north-south space requirement. On the right side there, we see our array of 3 rows, and notice we have F as in footprint, and D is what we just calculated, the distance between rows. And then you see another right triangle there, and that's how we're going to calculate the footprint of a tilted module. So I'll walk you through that. So to determine the total north-south space, we take the number of rows times the footprint of a tilted module, and then we're going to add the number of rows minus 1 times the distance between rows. That rows minus 1 means, we only have 2 gaps between our 3 rows in this example. So that's why we have rows minus 1. So here for 3 rows of modules, first we need to do the calculations within the parentheses first. In this case, it becomes 3 times the footprint plus 2 times the distance between rows. And again, going back to trigonometry, the cosine of angle A, which is the tilt of the module, cosine of angle A is equal to the adjacent leg over the hypotenuse. Our adjacent leg in this case is the footprint, which we need to determine. The hypotenuse is the module length, which we know from the module manufacturer. Cosine A equals F, the footprint, over the module length. We solve for F. We get footprint equals cosine A times M, or module length. Let's go through an example here. The footprint equals cosine A times the module length. In this case, our array tilt angle was 20 degrees. Cosine 20 degrees equals 0.94, and our module length, or M, was equal to 6 feet. So F equals 0.94 times 6 feet. So the one row's footprint is 5 feet 8 inches long. Again, that's represented by F. Our total north to south array footprint is again 3 times the footprint plus the number of rows minus 1 times D. We do each individual calculation, 3 times 5 foot 8 inches and 2 times 4 foot 10. We add those two together. We get a total north-south spacing of 26 feet 8 inches. And keep in mind, this is not including any space that might be required to the north or south of the array. Obviously, we haven't calculated, let's say, the east-west width of the array, but there's a lot less space between modules going from left to right or east to west in this case. So really, it's just the width of the module times 6 in our case. That would determine the amount of space required from east to west or left to right in this case. This is just the total array footprint. We don't have any additional space around the array, which might be required by your AHJ or access requirements. And finally, I mentioned earlier the trouble if the ground is not flat or if it's a non-horizontal site. In addition to rolling terrain, having different array orientations can pose difficulties and will require additional calculations for inner row shading. We're not going to get into that in this class. If you need to, there is modeling software like Google SketchUp, or there are some AutoCAD add-ons that can help you when you have varying array orientation and or rolling terrain or changes in slope of a site. In this lesson, we're assuming that the ground or the roof is flat. If you're on rolling terrain, you're going to have to look into some more advanced software. Okay, that's it for calculating inner row shading. Up next, we're going to look at the varying code required spacing to be around PV arrays. Thanks a lot. Talk to you soon.